All right, let's talk regression model validation. This is Dr. England, Module 13, Validating Regression Models. This is actually kind of the stuff that really gets interesting. So let's let it get interesting. First thing is that you should have already from the previous lectures known what residual analysis is. Residuals are basically the observed values for a regression model minus the predicted values. And it can tell you, hey, look, it really does actually do everything, kind of works from the residuals. You can determine if there's any real issues with the model by looking at the residuals. But let's talk about what statistics go with that. So one of the things that you really want to look at is the plots. The plots tell you a lot. I mean, so there's a few. Standard scatter plot is one of the biggest. You know, you take the, but you can also look at a scatter plot of the residuals with predicted, or you can look at the fitted versus the predicted. But you've also got these things, residual plots and QQ plots, and we're going to also look at an influence plots also, which are some of the ones that can give you information. And what I want to do is I want to do this with one of my favorite examples. This is the Dolbear's Law example, which basically says that the speed at which crickets chirp varies with temperature in a linear relationship. It's pretty cool. Now, what I would say is, and there's Dolbear's Law right there, but if you really want an interesting look at this, just Google CBS Sunday Morning crickets chirping or cricket thermometer, but it was on the CBS Sunday Morning show and with Robert Krulwich, and he does a great job of explaining Dolbear's Law. But it's a perfect idea. It's a perfect concept for looking at these linear, these relationships and understanding. But we can also look at this in a little bit more detail. So let's do this. This is the code, and I've actually got real data from cricket chirping that I hunted down, and I tossed it into Python. So these are some real chirps. These are the numbers, the temperatures, and the thing with this is that different species of cricket chirp at different rates. So it does kind of give you this. Now, I actually did a few mistakes here in the way that the code looks, but you know what? I'm not going to stop there and dwell on it. There's you've got a few imports that you need to do, but let's look at what the results look like when you're done with this. So here's the model you come out with if you do an OLS regression analysis. So we're not actually doing, we're doing ordinarily squares. We're not doing at least some squared errors, but it's still a good model. And the equation comes out to be y equals 25.2323 plus 3.29991 times x, which is basically saying the y-axis is at 25, and you're looking at basically 3 chirps per second as you increase every temperature in degrees Fahrenheit. And you can get the output of what the least squares give you. There it is. The model coefficients, which are right here. And if you look at the plots, which is really what we're doing this for, you can see the regression fits pretty, it looks like a pretty decent regression. It's not perfect, but it's crickets chirping. You don't expect it to be perfect. And then you've got the residuals. Remember, the residuals are the difference between the predicted and the actual values. Okay, so, and you can see this is what they come up as. Now, you want to check for different things, and so we're going to look at what you can check for. So there's a few statistics that I mentioned, and one of them was the Durbin-Watson statistic, which you're not, by the way, going to calculate by hand. Sorry, if you want to do it, you can look it up and do it. It's easy. It's one of the modules inside of the library. So you've got the Baruch-Pagan from Stats Model and the Durbin-Watson from Stats Model. Okay, Stats Model has both of those, and Stats Model is, and I actually just did it as SM because I want to make it easy to do. So you're going to be able to generate this code relatively easily to get these numbers. Now, the real thing is, what does the number mean after you calculate it? So you're looking at first order correlation. It's a simple test with two variables, and you got a Durbin-Watson statistic of 1.82. It's there's really no autocorrelation going on there, and you also appears to be homoscedastic because the p-value being greater than 0.05 and the LM statistic being 2.837 basically means the null hypothesis is that there's no relationship. We've gone ahead and gotten rid of that null hypothesis. We've basically said we're rejecting the null hypothesis, so there is definitely a relationship there. And the data, the residuals appear to be homoscedastic, which I've defined in the last lecture, so I'm going to just keep going because I'm trying to make this short. Now, if you look at the QQ plot, which you definitely want to do a QQ plot. QQ plot is where you basically take all the numbers, you put them in ascending order, and you plot those and look to see how those guys look. That is this guy right here. But the other thing that you can do is an influence plot. An influence plot is also one of the options that you can just simply say, hey, I want to see an influence plot. Give me the code to do it in Python with the data. And what it tells you is that which numbers, which of the individual points has the greatest influence on the model. And every now and then you're going to just see something that just jumps right out and says, well, this thing is in the model's got a huge influence based on 1, 2 numbers. When you see outliers, you're going to see this actually occur. It's the size of the circle. That's the influence that you're looking at. So any one of these circles that's way, way, way big is going to be a big influence. Now, numbers that actually lie right on the line in the fit are typically going to have a low influence, and the numbers that fall further away from it are going to have a larger influence. But you can actually, it's good to see if something is really making a big influence on that. And in the situation of doing cricket chirps, you could actually look and say, well, is this a different species of cricket? You can look at it and say, maybe these really don't seem to fit the data, but why? Remember, every time you do this, it's specific to the type of problem that you are solving. So you need to know that. So, what do you do with the residual analysis? You look at it, you can fit the regression model, you calculate the residuals, and you actually just get a visualization of the residuals. But if you go back and look at that, it may not say a whole lot to you. It doesn't say normal, but remember, you can fit it to a histogram to see if those things look normal. That's another one that I didn't do because I did it in the last lecture, well, in 2 lectures ago. But you can definitely do that QQ plot, which tells you a whole lot. And that's what you want to look at. You want to say, hey, is this really a good model? Because it's not about the fit. It's about the model. Right, so you want the best model possible. And looking for these things that say, hey, this isn't a good model is what you want to do. So let's look a little bit at that influence diagnostic. So it really just tells you one thing. How much influence do the individual points have on the model? And if you see points that are just totally disproportionate, you can say, you know what, let's look at that point. Maybe we toss it. And that's something that you can do. And as you saw, that influence plot makes it really easy to see these things, to see which ones actually have that high level of influence there. Let's see. When you're doing influence, what pieces actually mean something? Now, we're not going to go into that much depth on this because it's kind of getting above and beyond. I do want you to know that these things actually are that there are ways of looking at them. So you're looking at how far does any independent variable deviate from the mean from the mean, and they can have a higher influence. Cook's distance is a number that you can actually calculate, and you can look at whether that when you see a high Cook's value, you can see that those values, hey, they have a high level of influence. And the defits, which also can do the same thing. So essentially, there are statistics to measure the individual the influence of individual points. And when you're doing these fits, and you're really working with real data, you really do have to look at, is one value or 2 values influencing my entire fit? So what do you do for this? You set up the model as you did before. You fit the regression. You can use OLS. And then you calculate the individual influences that are in there, and then you make decisions. You've got specific metrics now that you know that you can use. There's 3 of them. There are more. They're not the only ones, but you want to know if something is having an undue influence on the model itself. Okay, and I'm not saying keep it or throw it out. I'm saying look at it and understand, does this point really need to be in the model? Now, we're going to talk a little bit about transformations, because we've only dealt with a nice little linear equation, y equals mx plus b, but there are other ways of fitting. There's other types of curves that you can fit to, and these are called transformations, and they're really actually kind of easy. I almost always, I mean, if it fits a linear perfectly, but that's rare that it actually fits linear. It might fit e to the x, beta naught times e to the beta 1 x might be the actual fit that fits it best. Well, that doesn't fit that's not a linear regression. Well, actually, in reality, it is a linear regression with a transformation. So let's talk about some of the transformations. Here's a few: log, reciprocal, square root, box, Cox. We're going to actually I'm going to just show you what those look like just for those, just so you understand, because these are 4, and these are common. How many different types of transformation techniques are there? Well, there's I wouldn't say it's infinite, but it's pretty large number of transformations that you can actually apply to the curve to try to an equation to try to see what types of what might fit better. So now for the transformations, there's actually, you can actually do a transformation of the data directly. Like if you have a variable x that is an array or numpy array, and you do numpy log x, it's going to give you a numpy array of all the values that are actually the log of x. That's kind of nice and easy. These are just different ones. And when I go back and when I show you some of these transformations, you can either go ahead and just do the transformations directly, but there are ways to do the transformations directly in the Python code. The important thing isn't how you do the transformations. They're not hard to do. The importance is understanding the transformations and then looking at the final curve fit to see if it makes sense. Like if you were to plot something and it's obviously an exponential curve, there's no point in trying to fit it into a linear curve. You would use an exponential equation. So what do those kind of look like? Well, here's the model that you guys have been using all along. Y equals beta naught plus beta 1 times x with the residual. But what happens when you transform it? Well, let's look at a transformation like the log transformation. Look at this. It's actually y equals beta naught times x to the beta 1. That is a log transformation. And you say, well, how do you get beta naught and beta 1? Well, it's just a simple transformation. And actually, you can look algebraically how to convert this into that standard form of a linear. It is doable. Take the log of both sides, and guess what? You're going to find that it's a relatively simple transformation of the y data and the x data. It's actually a little bit easier to see with some of the other transformations as you go through. So let's look at this one, the reciprocal model. Well, in the reciprocal model, the y isn't transformed at all. But all you're doing in the reciprocal model is replace x with 1 over x in every single instance of the data. That's your transformation. You can calculate the beta, and that's going to be your final form of the equation. Y equals beta naught plus beta 1 over x. But to do the fit, you need it in that form, y equals beta naught plus beta 1 times a value. And what you get to do that value, because remember, you can fit this easily with some squared errors. This is easy to do. Well, what do? You just replace x with 1 over x, find beta naught and beta 1, and then there you go. There's your final equation. Realizing that the residuals go with that. What other ones have you got? The square root model. That one you should be able to, now looking at this, you should say, well, what is the transformation? Well, it's really not that hard. It's replacing y with the square root of y and then actually looking at fitting the model. And then you can easily just square now both sides if you want to get it in terms of y. Okay, because square root of y times square, squared is y, and then you would actually have this entire term right here squared. One of the common ones is called the Box-Cox transformation. And again, it's a transformation of y, and it's y to the lambda, and you need to have a lambda coefficient. And notice that this only works if you're looking at positive data. Now, you do have a transformation that deals with y being exactly, if the lambda is 0, then this transformation is just that the y is the natural log of y. You can also, by the way, show that algebraically. I'm not going into that much detail with this. I want you to understand that when you do a transformation, you simply take all the x or all of the y or all of the x and all of the y, and you apply a transformation function to it, and then once you get it into this specific form, okay, this a value equals beta naught plus beta 1 times a value plus the residuals, you can calculate the beta naught and the beta 1, and then you can untransform this data back and get the final form of the equation, because the beta naught and the beta 1 aren't going to change. Okay, that's the case. And so this is just another common transformation that you can do. That is really it. And those are some of the most common transformations that you're going to see. And the nice thing is if you're using the Python packages, the transformations aren't that hard to do. And it's also not that hard to do if you're actually using, because I do say, why are you going to write the code to do a transformation of the data? You just say, you know what? It looks to me like this is going to fit a log transformation. Can you do a log transformation on the x and then calculate these values? And you're going to get the code to do it. And then you can run it in Python. You can look at it. You can plot the residuals. You can plot the final form of the equation. You can look to see if it fits. It's not, that is all relatively straightforward to do. Understanding that you have the ability to transform the y's and the y and the x by applying a transformation function to them. Cross-validation is looking at the performance of the model. Realize that there are a lot of ways to say, hey, let's say we've got a ton of data and we go, I can split this data up into a fit, and then I can see how well that fit actually works on the data that I didn't do it with. So I've got that. So you've got a number of types of cross-validation methods. One of them that's very common is called the k-fold cross-validation. And in that case, you just break it up into a number of subsets, and then you do the training, which basically the training means you're going to get the parameters with one set of data, and then you've got a testing with another set of data. The other one where you just go through and you say, okay, let's just knock out a number, let's see, and let's just repeat it. Let's just take every single observation and see if any specific number, if we leave it out, what happens. So you've got, you're basically using a one number as the validation and the other numbers as the actual model fit. And then there's another one, which you, by the way, are probably never going to do, which is the stratified k-fold. But I want you to just know that there are these types of cross-validation techniques. Now, when you get into the world of doing fit with AI, it becomes extremely important because you always do this. But remember that the fitting of a neural network model, which looks a lot, but by the way, neural network model, one of the models that you can do if you have a single neuron, and two nodes in a neural network model in AI, it's your standard linear format. It goes right back to that. It gets way more complex because in those models, but the training is mathematical techniques to get the parameters, and what we call them in the AI world is we call them the weights for each of the individual variables that can go in there. So a little bit of simplification, but it is essentially the same. You're looking at the same thing. So in this case, you're really saying, hey, there's ways to validate it by taking some of the data and putting it over here for testing and some of the data over here for fitting, and there are different techniques to do that. what you would do if you're doing cross-validation is you probably would consider multiple versions of the cross-validation. They're built into the models. So, I mean, they're basically built into the statistical libraries that you're going to use. If you really want to go through and understand how the calculations work, it's not actually that terribly difficult to do, but it is incredibly tedious. Now, I gave you an example, I think in lecture 11 of a confidence interval. And if you were paying close attention, you would have noted that the confidence interval, most of the points were living outside that confidence interval. Well, because in regression analysis, you use something called a prediction interval. It's going to be wider than a confidence interval. And it looks, because you've got different levels of variability, because you've only got two parameters. And it really does give you a realistic set of boundaries for an actual regression fit. So, the formula is right here, but it's also very straightforward to actually just tell the model, the stats model, because you're going to be doing this with program anyway. Tell the stats model that you want to do the prediction interval, and the settings are typically 90, 95, and 99. And if you put it all together, you're basically going to fit the model, you're going to come up with all your predictions, and then you're going to actually do the calculation of the intervals. And what does it look like? That's really what it boils down to. Remember our crickets? This is the that was real data, and this is the 99, the 95, and the 90% prediction intervals for that exact same set of data with the different shades of gray associated with the different ones. The 99 is the outside, and what it really is saying is that you would expect that 99% of the data that you have in the collection would fit inside of that 99%. So if I had a lot more data, I might actually have one that's outside of it. Or there could, I mean, there's still a good possibility that you could have one with the limited, I think there's 15 data sets, data observations here. There's still a possibility that one of those data observations would be outside that 99%, but because remember, it's 1 out of every 100, essentially you're saying is going to be outside of that interval. And then you've got your 90, 95, which is a little bit tighter, and your 90, which is a little bit tighter, and then you can kind of move down from there. So really looking at what can you do to actually, the goal is to get the best fit possible. Now, I am only going to talk about, because I'm not going to have you doing a multiple regression model. It's not going to be in your homework. It's not going to be in your quizzes. It's not going to be, well, I can't remember if I put any quiz questions on it, but and when I take it back, I think I did put one or two in your quiz questions, but it's not actually having you do it. So what can you do in the validation? Well, you've got different ways of looking at the residuals. You need to know what a residual is. You need to know that, you take the observed, you take the predicted, and the difference of those is important. You can look at the influence. Now, when you're talking about the influence of any individual point, do individual points have undue impact on the model fit? You've got the ability to say, you know what, maybe the beta naught plus beta 1 times x is not your best curve for this, and you can still use the methods that you've got by doing transformations, because it's just a conversion by transferring the data, one of the data, the y or the x, within that model. So it's a transformation model. You've also got the ability to look at the cross-validation, to look at one set for one set for the other, one set for the development of the model, one set for looking at that, and then actually looking at those different models. So and then picking out the best model as you go through and do this. And the last one, which is calculating the prediction uncertainty with that interval, basically your prediction intervals. All of those are ways to look at how to best get the best model. And it really is worth, if you're doing a regression analysis, typically one piece of data, one dependent, one independent, it makes good sense to actually do good validation. That's it. I'm going to give you one last thing. There's some key takeaways here. Residuals, influence diagnostics, transformation, cross-validation, and prediction intervals. Okay? So, they should all make perfect sense to you. I'll leave the slide up as I go through the last 30 seconds of this. Wow, I got to 25 minutes. I was expecting to take a lot less time, but sorry about that, guys. I went through pretty fast, though. So, yeah. Anyway, have a good time. Have a good day.